Hello everyone, welcome to a lesson on electromagnetism. This lesson begins with a question that Faraday had based off his own discoveries while researching E and M. And the major question he had was a reversal of one of his discoveries, all right? And it's a discovery that we've already seen. We know that current makes a magnetic field. All right, we know that a current is a magnet. All right, we've seen the equations and we've seen proof of it. So and remember, Faraday was the one who kind of figured that stuff out. Now Faraday is going to switch that question around. All right, now he wants to see if a magnet can make current. All right, so remember, this is what we've already seen. We know that a current makes a magnetic field. We've seen it. All right, in other words, we put in symbols. An I can make a B. An I makes a magnetic field, and we've seen the equations, all right? So we're going to switch these things around. He wants to know, Faraday wants to know, if a magnet can make a current. In other words, can a magnetic field create currents, all right? So, of course, we're going to try that. So here's a diagram of what Faraday made to test out his idea. All right. What he made is we have a battery here, all right, supplying voltage, which gives current through here. And in this wire, there's a switch. If he pushes the switch down, all right, it completes the path for the current, and therefore we get current through there. If this switch goes up, there is no longer a path, and the current can't get through there. All right. Now with this red wire here, he wraps it around an iron ring, and we've seen that before. We've done it, and that will make this thing an electromagnet. This current will create a magnetic field in this iron ring, making it a magnet. All right, but then on the other side of this magnet, he's going to take a totally separate wire, all right, and connect that wire to an ammeter. Now these two things are insulated. It's probably rubber or plastic or whatever he decided to use, so that the current from here can't jump through the metal into the other one, all right? So these things are two totally isolated circuits, and the only thing that will connect them, or that will relate them, is the magnetic field in here. The idea is this thing will make a magnetic field, and the magnetic field in the blue will make a current here, and we can see that with an ammeter, all right? So let's test out Faraday's idea for real. We're not going to do the exact setup. We're going to do something closer. Instead of using a battery or voltage supply to create current to make a magnetic field, we're going to skip right to the magnetic field, because remember, that's the big test. Can a magnetic field in this loop here, in this coil of wires, create a current there? All right, and that's what we're going to try for real. So let's see how that works out. Okay, so here we are testing out Faraday's initial idea, and instead of using a voltage source where we can make a current that makes a magnetic field that will make a current, we're just going to skip right to it and make the magnetic field. We're going to see this magnetic field, which you can see with the magnet here, is inside our loop of wire, and that loop of wire is attached to an ammeter. All right, and hopefully, like expected, you can see that a magnet with that makes a magnetic field inside a coil does not make any currents. All right, so it's kind of a complete failure. All right, a magnetic field does not make current, which should make sense. All right. Okay, we've put Faraday's question to the test, and turns out that it doesn't work. It was a complete failure, and that shouldn't have been any surprise. All right, you should know that just a simple magnet cannot create electricity. If that was the case, climate change wouldn't be an issue. We would have electricity at our fingertips all the time. And we know that's not the case. We have to, burn gasoline, do all this other stuff. So you should know that if you had your phone here, that's not a phone, just an iPad, iPod, because that's what I use all the time. You should know that you can't charge this iPod just by taking a magnet and wrapping the charging cord around it. All right. Maybe you try this. All right. Good idea. Faraday tried this, but you should know from experience that this does not work. This thing is not charging up just because I wrap a magnet around it. It would be awesome, all right, because then we could just make electricity from a magnet. We can make electric motors just from a magnet. We can move our cars without buying gasoline just with a magnet. We could power and our entire house with just wrapping cords around magnets, but unfortunately that doesn't work, all right? So back to the drawing board for Faraday. Fortunately for us and all of humankind, he was extremely smart, extremely hardworking, very persistent, and could work experiments to figure out what was really going on. So let's take another look at Faraday's idea and see what happens. Okay, so we go back to his setup. He starts playing around with this thing. Obviously, he's got to be disappointed that when he turns the switch on, nothing happens over the ammeter. So he turns it off. But this time when he turns it off, it's the strangest thing. When he turns it off, as he puts the switch from on to off, the ammeter over here spikes. Well, that's very strange. If an ammeter shows anything other than a 0, that means there's current there. Well, he said, well, maybe that's just a fluke. Something interfered with this thing. You know, this is back in the 1850s, if you will. So maybe the laboratory said it wasn't completely isolated, all right? Maybe it's a fluke. So keeps experimenting with it. This time he turns it on, and when he turns it on, now he's paying attention to the ammeter, but very, very closely. When he turns it on, the ammeter spikes again, but it goes back to 0. So now the thing's on, nothing's happening. We've already seen that. Goes to turn it off, the thing spikes again. And that's significant because every time that thing spikes, that means there was current going through there. So he keeps playing with the thing. Turns out every time he turns it on and off, that process, when it goes from on and off, gets current. All right? And that is a monumental discovery for the human race, for humankind. All right? It puts us on the path to what our lives are now, all right? And before we just take this as a great story and then, yeah, this is good, let's prove that this actually works. Because if we can't prove it, this isn't science. This is just nonsense stuff, all right? And we know now in the time of the coronavirus, science is very, very, very important, all right? You have to be able to prove it. You can't just look on Facebook and Twitter and become a scientist. You need to be able to prove this stuff. So let's go back to our setup and see what happens, see if we can replicate Faraday's results. All right? Okay, so now we can test out Faraday's idea of maybe a changing magnetic field, all right, making a current, all right? So instead of turning a switch on and off, which will make an on and off magnetic field in here, we're going to skip right to the point and try to make an on and off magnetic field in here and see if it makes current, all right? Now remember, in this ammeter, if it points anywhere other than 0, that means there's current going through there. All right, so how do we get a magnetic field to go on and off inside here? Well, we just take our magnet and we put it inside and we move it outside. If we put it inside, there's a magnetic field inside. To turn the magnetic field off, we just take it out. And let's see, as I move this magnet in and out, pay attention to the ammeter over here. All right, so check that out. It's pretty wild. Think about what you're seeing here. You are seeing me make electricity without a battery, all right? If this was a light bulb, you'd be able to see that light bulb go on and off. And I'm doing that with just a magnet. And that is pretty crazy, all right? It's an unbelievable discovery in physics that you can create current without a voltage source, all right? Essentially, you could think if this was a light bulb, I'd be turning this light bulb on and off without a battery and just by moving a magnet in and out, which proves Faraday's experiment correct. All right? And we can see that in real life here. Pretty awesome. Okay, now that we've seen this incredible discovery that you can make electricity from a magnet, let's kind of summarize Faraday's experiment there. All right? So we know that just a magnetic field will not make current, all right? We proved that didn't happen. But in the experiment, when we went from off to on, that meant this current that we created, and I'll show you in this diagram here, this current here that I'm talking about is the initial current that we are making from this one. All right. So when Faraday turned that on, from going from off to on, that made a magnetic field that also went from off to on. And that magnetic field that went from off to on made current. Now, once we had current on, we had a steady current, we had a steady magnetic field. And a steady magnetic field did not make any current. Then likewise, when we went from on to off with our current, that made an on to off magnetic field, and that gave us a current spike. All right. So to put this in a little bit more mathematical terms, all right, if you just had a magnetic field B, you got no I. All right. A magnetic field does not make a current, but a changing current makes a changing magnetic field, and that changing magnetic field made a current. Now remember, this current spiked, but in general we got current. All right. Current that made a magnetic field did not make a current because this magnetic field was not changing. Remember, these deltas represent change. So a changing I made a changing B, which made a changing I. All right. And likewise, it didn't matter which way the change was, if it went from off to on or on to off. If it was a changing current, all right, that makes a changing magnetic field, which produces a current. So what's the big story here? A changing magnetic field can make current. A changing magnetic field makes electricity. All right, that's the big takeaway that you can get from this. All right, so let's get a little bit more details here, because this might present a problem here. All right, if you're an advanced thinker. All right, so let's look at that problem. Okay, now that we know a changing magnetic field can make a current, all right, let's look at the consequences of that. All right. Remember, a current is moving charges, so that's a changing electric field as well. But let's think about this. All right. If we have a changing magnetic field, all right, we saw that made a changing current, and we know it's changing because the thing spiked. All right. If I kept changing that magnetic field in one direction, it would continue to change that direction, and the current that we get would keep on going big. All right. So, but now think of what a changing current can do. A changing current makes a changing magnetic field. What does a changing magnetic field do? It makes a changing current, and so on and so forth. So it seems like this could be a never-ending cycle. We could take a magnet, put it in a coil, and if we change that magnetic field, then the current inside the coil would change, which creates its own magnetic field, changing magnetic field, which then adds to the current, which creates more changing magnetic field, so on and so forth. And it'd be like we'd have free energy. All right. And unfortunately, that is not the case. All right. We saw experimentally when I put the magnet in there, it changed the magnetic field, it spiked and went back down to zero. It didn't keep multiplying on itself. All right. So the question is, why? What prevents that? All right. And I'm going to show you the answer here in a sec. And I'm going to show you a demo that kind of proves the reason that this is happening. All right. Okay, so the reason why we don't get never-ending energy, the reason why the chain of changing magnetic field, the changing current, the changing magnetic field breaks is something called Lenz's Law. All right. And the idea is basically this. All right. The changing magnetic field will make a changing current. This changing current then makes its own changing magnetic field. Remember way back into magnetism. Magnetism comes from moving electric charges. So if I have a current makes a magnetic field. But if I have a changing current, that makes a changing magnetic field. Now, what prevents this from multiplying itself is the direction of this goes against the direction of the original change. All right. If this one went, let's imagine this one went from on to off. All right. Or let's go the other way. if this thing was off to on, all right, the original one turned off, it was off, turned on, then this one, they would make that current, and this current will make a magnetic field that will go from on to off, essentially canceling out this original one so that it doesn't keep multiplying, all right? And that's a hard idea to wrap your brain around, but you can see the effects of this, all right? Okay, so here's a demo that kind of illustrates Lenz's law, the idea that it produces a current, it produces a different magnetic field. All right, here is a copper tube, all right, and a metal ball, all right, no secrets, we can see right through it. If I push this through there, it goes very fast. It's in free fall. We've done all those calculations just like you would expect, all right? But then, all right, and if I can go here, you may be able to hear it, all right, goes through free fall. But now, if I take this ball, it takes a while for it to go through, all right? And why is that the case? All right, well, this is a magnet, all right? And you say, well, that makes sense. It's just sticking this in. But remember, copper is not magnetic. This thing does not stick to this, all right? You notice I can't pick this. This is not magnetic. I know it's metal, but we know that's, see, this does not stick to this. We know only a few metals are magnetic. So how does this work, all right? How does this work? Okay, so here's an overhead view of the scene demonstration. In this first one, we have the regular non-magnet metal ball, and we see it just goes through in free fall, all right? But then if I take the magnet and put it through there, it's a very different result, something that you might not expect. All right? So it doesn't just stay right along the side, it kind of hovers through there. And I'll do that again so we can see this one more time. Notice that it doesn't just stick on the side, all right? It stays kind of right in the middle and kind of floats. It's a very weird thing. All right, very cool. Okay, this demo is another illustration of what we just saw with the copper tube. All right, we have three different metal poles here. All right, plastic, I believe aluminum, and then copper, all right? And this is a magnet. Inside here is a magnet. All right, if we put it on the plastic, the non-conductor just goes right down. All right, just goes right down. And on this middle one, goes down slower. And then on the copper one, takes a while, all right? Takes a while. Compared to this one, and then certainly compared to that one, which is just free fall. All right, so why is this happening? The answer lies within Lenz's law, all right? And our ideas of magnetism creating current, which creates magnetism. So as the magnet falls through here, all right, on the inside, surrounding this thing is a magnetic field. So there is a changing magnetic field in this tube as this thing moves, because the thing is moving through it, all right? That changing magnetic field makes a current in this, all right, in this coil, all right? See how there's a path for the current to go around. So the changing magnetic field caused by this will make a current through these coils. It is just like Faraday's experiments, just like the experiment I showed you. The only difference is there's no wire leaving here to go to an ammeter, all right? So the current just goes around here. Now, that current that's going around here makes its own magnetic field, all right? And that magnetic field will go against this one, all right? Essentially pushing it back up, repelling it, all right? If it went to it, it would increase this thing and make this thing go faster, but it doesn't. It goes against it and repels this thing, all right, as it goes through there, all right? And that's proof that Lenz's law exists and why that chain's broken, okay? Now, you may have one final question after we've seen all this, and that is, what about Ver? All right, we spend a ton of time going over our household circuits, learning about electric potential, difference, voltages, batteries. Is all that stuff invalid now? Does Ver not matter because we can make electricity, make current from magnets? And the answer is not quite, not really, all right? So the idea of a changing magnetic field making current is fine. That's the concept I kind of want you to get, all right? That's the most important part. But technically, there's a step in between, all right? And what we say is, the changing magnetic field does not make current directly. What it does is the changing magnetic field creates something we call EMF, which stands for electromotive force. All right, EMF. So a changing magnetic field will make an EMF directly. All right. And what an EMF is an induced voltage. You can almost think of it as like a fake voltage, as a virtual voltage, if you will, but it is an actual thing. And we think of it as an induced voltage because the units are volts, all right? So what happens is when you say, well, what about Ver? All right, what about Ver? Well, it turns out that delta B, a change in magnetic field, creates an EMF, all right? And this EMF is the V inverter. It acts like the V inverter. If we don't have a battery, we can make some coils, or we can get a magnet, we can move that in and out, and that's making the voltage, that's the V inverter. And we all know voltage creates current. So you can think, we kind of showed the bigger side, we skipped these things, but we showed that this makes that, all right? And the technical answer is, well, this creates an EMF, which is a voltage, all right, which is a voltage. It has the units of volts, and that EMF is actually what creates the current. So we're not bypassing Ver, all right, mathematically and technically. Conceptually, it's okay to think, oh yeah, changing magnetic field can create a current, all right? And I'm going to show you one last proof of that before we go, because it's okay to see an ammeter, it's okay to see these copper tubes with these magnets, but let me show you like that a changing magnetic field can create current in the easiest demo possible. All right? Okay, in our final demo for electromagnetism, all right, we have here a flashlight, but this isn't a normal flashlight. Most flashlights, they really serve one purpose, and that is to hold dead batteries, all right? It's not to light up, it's not to see in the dark. If you go find a flashlight, not the one that I'm talking about on your phone, like a real deal fat flashlight, go in your house, the first flashlight you come across, I guarantee you just have dead batteries. And that's kind of the purpose of flashlight, is to hold dead batteries, all right? You don't believe me, go find one right now, guarantee you turn that thing on, the batteries would be dead. This one, batteries would be, is a little different, all right? It doesn't have batteries at all. Well, then how would it work? That would be the $1 million question. All right, well, notice now it does not work, all right? All right, you may see right there's a reflection of that's coming from the windows. But if I hold it here, all right, and move it a little closer, all right, you can see the light start to light up, all right? So I'm creating light through in here by creating current. The current goes to the light bulb and the light bulb lights up. Now, how does that work? All right, if we look on this side, all right, right here, we can see that sparkly thing. As I press this down, that sparkly thing starts to move. Well, that sparkly thing is the sticker that's on a magnet, and now the magnet spins, all right, when I press this thing. So we have a moving magnet, which makes a changing magnetic field, because the magnetic field spinning all over the place. And on this side, you can see the two coils, there and there. And in between here is the magnet, all right, which you can't, it's hard to see spinning now. But as this magnet spins, the magnetic field located inside those two coils changes. Change in magnetic field creates current. Those wires go into the bulb, and we get light. All right. Now, the trade-off is I have to keep doing that, but it's an incredible idea that we can create current, we can create electricity without a battery, without a voltage supply, and all we need is a magnet. All right. awesome idea, life-changing, not just for me, but for the entire human race, a life-changing discovery that led to our current lives now, all right, which we should definitely not take for granted ever, all right? So, yeah, thanks for watching. That concludes this little lesson on electromagnetism. We'll see some applications of that going forward. Yeah, so thanks for watching, and see you when I see you.